Okay, so in this video, we're going to take a look at a specific context with some of the things that we've met already. So in this video, we're going to be talking about our average speed, instantaneous speed, our average velocity, our instantaneous velocity. But we're also going to talk a little bit about vector addition and some of the other things that we've looked at. This is really nice because it brings it all together. So what we're going to focus on is the speed and velocity when we're describing gas particles. So let's start off with a couple of things that it's worth recapping that we are going to be using in this video. So I'd like you to pause the video, grab yourself a scrap piece of paper. Can you answer these questions? And I've given you some clues as to some of the keywords I'm going to be looking for in the answers to these questions. Okay, so I'm going to assume that you have now paused and had a go. So let's see, first of all, what is velocity? So velocity is short for instantaneous velocity, is the rate of change of displacement. Okay, so you can see these are the key things that I was looking for that were indicated by those letters. Or alternatively, we could have gone for the gradient of a displacement versus time graph. That would be essentially the same thing. So then we're going to look at, well, okay, so what's average velocity? How is that different? So an average velocity is the displacement divided by the time taken for that displacement to occur. Okay, so again, we've got our displacement divided by time, essentially, our key things in there. So some similarities between speed and velocity. So let's start off with some similarities. Well, they are both measured in meters per second. It would be a fairly similar way of doing it. So differences. So speed is scalar, velocity is a vector. I don't think you can be scalar. I think you have to be a scalar. And the other thing we might put in here is, actually, no, that'll do for now. We don't want to be overcrowding ourselves with detail. That will do for now. So let's focus on the topic at hand, looking at speed and velocity in a gas, and looking at the particles in a gas. So here I've got a PhET simulation up, so you can have a play with this yourself if you go to the website PhET and search for gas properties. So in here, what we've got is a model showing all the gas particles, and we're going to look at just describing speed to start off with, and we'll come to velocity later on. So if you observe this closely, what you'll notice is that some gas particles are moving faster than others. Okay, so although we have all of these particles reasonably fast moving, you will be able to find some slow moving ones from time to time, but we've got a range of different speeds going on there. So the particles transfer energy when they collide. So you can see that one might be going quite fast, it will then hit one, and then it will be going slowly, so it's clearly transferring some energy away. So let's see the effect of if we increase our temperature, and let's increase it quite a lot to make it quite dramatic. Let's return the lid. If we increase the temperature, the speed of the molecules increases. Might be something else that we can discover there. So that will do for now in terms of describing our speed. This is the key thing I want to pick up, that some of the particles are moving faster than others, and the effect temperature might have on the speed. Okay, so let's dig into that a little bit more and look at how we model the gas particles. So we use something called a Maxwell-Boltzmann distribution, like you can see here. So what we've got is on the x-axis, we've got a speed that a molecule might be at, and then the y-axis tells you the number of molecules you have at that given speed. So what we can see here is, first of all, when we say speed, we're talking about instantaneous speed. So this model here actually comes from statistics. So we're using statistics and probability in order to produce this model. So what can we see? So we can see that there's a very low probability of being at low speed. How do we know that? Because not many molecules are at that speed. You can also see there's a very low probability of being at very high speed, because we can see not very many are there. You can see most particles tend to be clustered around this middle section. So the majority of your particles, I would say, would be somewhere around these kind of speeds here, but there are some at the extremes in here. So that's what we're essentially seeing in here. You will see most of them are somewhat in the middle at sort of this middling kind of speed. But you can find some that happen to be traveling particularly fast and some that happen to be traveling particularly slowly. And you can kind of see this distribution in action. So this is how we describe the instantaneous speed in a gas. We have a range of different speeds, but some are more probable or more common than others. So we get if we want to instead describe the average speed, what we can do is think about, well, how is that affected by changing the temperature? So what I'm going to show you here is what these distributions look like as you change the temperature. And as it says here, the high green one is a higher temperature gas than the red one. So in terms of describing the average speed, what we can see here is that the average speed increases when we increase the temperature. But if we look at the instantaneous speed, we can still see we've got some particles with quite low speed. So we haven't increased the instantaneous speed of all the particles, but what we have got is a much larger number of particles at these very high instantaneous speeds. So the higher your temperature gets, the larger number of molecules you get at this very high speed end, and that's what's increasing your average speed of your gas particles, the increase in the high instantaneous speed section of your graph here. And we could keep increasing the temperature, and this sort of peak would shift further and further and further to the right on here. And the other thing to spot is that the peak actually comes down as your temperature goes up, and that trend will continue to occur as well. And that's because the area under this graph stays fixed, because if you add up all the probabilities, you have to get 1. So actually, as we shift this graph and we make it wider and wider, we actually end up with the peak coming down to keep the area the same, because probabilities always have to sum to be 1. Okay, so that's instantaneous speed and average speed. So instantaneous velocity is quite easy. So we know that velocity is how fast something's moving, but in a specific direction. So the magnitude of instantaneous velocity follows exactly the same distribution as speed does. So on here, I could very easily just go, nope, not speed anymore. This is now velocity magnitude. Again, like measure meters per second. But the additional thing to note about instantaneous velocity that we don't talk about with instantaneous speed is that the particle's velocity direction is completely random. So there's no way we can predict what direction a gas particle will be moving at a given time. It's purely random. So that produces interesting effects when we start thinking about the average velocity of a gas particle, or even of the whole collection of gas particles, if you like. So intriguingly, if you calculate the average velocity of a gas particle, it turns out to be 0. So that comes across as fairly strange. If we go back to our simulation, we're like, no, these particles are moving around. How on earth do they have an average velocity of 0? So let's actually think about that in a bit more depth. So let's consider a particle, and over a period of time, it had the following 8 velocities. So it's quite a simplified example, but it gives you the right idea. And because its motion and direction are purely random, it's reasonable to say that it spent an equal time at each of these velocities. So we don't know what order it would go through those in, but it would spend equal time at each of them, and each of those velocities are the same magnitude. So what happens when we add all of those velocities together? Well, as we've seen in the videos I've done on vector addition, if we want to add vectors together, we arrange them tip to tail. So that's what I've done. I've taken all of these vectors. I decided to start with this one pointing to the right, so you can see here, and then I just followed it round in sequence. And you can see that once you add all of those vectors together, you end up exactly back where you started it. We've formed a closed shape. And that means if you add all the velocities together, you will get a value of 0. So then when we divide that by the number of particles or whatever, that number still comes out to 0. So in a gas, if you take an individual particle and you monitor it over a long enough period of time, its average velocity sums to 0. And if each individual particle has an average velocity of 0, by definition, that means the whole system of gas also has an average velocity of 0, despite the fact that some of those particles will be moving at very high speed. Some of them, like gases, typically you'd get sort of 500 meters per second, something like that. You can get reasonably fast moving particles, but they still have an average velocity of 0. Okay, so what I want to do is just go through some summary questions to see if we've picked up the key things we were looking at in this video. So what you need to do is grab a scrap piece of paper if you can, and pause the video and have a crack at these 5 questions here. So starting off with sketching some graphs of what the speed distribution looks like, and then what we'll do is then have a look at describing what's going on. I realized I was sloppy and used a V instead of an S. Okay, so have a crack at these and then we'll see what we should have here. Okay, so I'm going to assume you've had a crack now. So let's sketch our graphs. So let's do a low temperature one to start off with. So the key things that we're looking for is there's very few particles have low speed, very few particles have high speed. Most of them are clustered in the middle here. This distribution, by the way, isn't symmetrical. It stretches much further to the right than it does to the left, typically. And if the temperature increased, let's do that with red. The things I'll be looking for, so it still starts down here at the bottom. The peak is to the right, but the peak is lower and it should extend much further along on the x-axis, something like this. So this is higher temperature. Okay, so now we're going to describe what these graphs are actually showing about instantaneous speed and average speed. So let's do instantaneous speed first of all. The graph shows that for a gas, there are a few particles with very high or very low speed, and most of them have a speed somewhere in the middle. So that's what it shows us about instantaneous speed. So, and if, I've switched into caps, if temperature is increased, the number of particles at high speed increases, and that in turn means that the average speed increases. So once we start modeling gases, we might get to this in this video series, we use something called a root mean square to quantify sort of like our average kind of speed. It's not exactly the average, but it's a useful form of an average. But that's what we're seeing from these graphs. We've got these range of speeds, but we can change what that distribution looks like if we change the temperature. Okay, so then what we say, well, what can we say about the instantaneous velocities at a given temperature? There are 2 things. So the magnitude follows the same distribution as speed. The direction of gas particle velocity is random. So there's no way of predicting what direction it will be at any given time. And then finally, what can we say about the average velocity of a gas particle? It is zero as long if you measure it over a long period of time. So if you measure it over a very short period of time, it's possible to measure it to be not zero, but if you leave it for a long period of time, let all of the random variations occur, then it ends up averaging as zero, which means the average velocity of all the gas particles is also zero. And once we take a look at Newton's laws and in more detail, we'll see that that kind of makes sense because the gas as a whole is its motion isn't changing. The gas isn't sort of accelerating or anything like that. So that kind of makes sense when we think it on a large scale as well. So that's where we'll finish off looking at this video, looking at speed and velocity in gases. And then in my next video, I'm going to start looking at acceleration, which is the vector quantity we haven't looked at so far in this video series.